When people think about the most dramatic things in space, they tend to go immediately to black holes, which are absolutely incredible. Out of control gravity that can actually suck light back in. It's just amazing. But I think neutron stars deserve a little more love, because a neutron star is also created when a massive star dies, but it doesn't have quite enough mass to actually collapse into a black hole. It actually leaves behind a thing, a physical thing that you can study. So while black holes are this bottomless pit, with neutron stars, you have this very strange thing that you can look at them, you can observe them, you can take real measurements of. And you're looking at something that is mind-blowing, and in some ways our physics really isn't ready to describe yet.
The extreme power of neutron stars.
To me, I think one of the most amazing things about the universe is the question, what is energy? And this can go very, very deep. A lot of us are familiar with, energy it takes energy to accelerate something, like, to actually throw a softball. That takes, energy, chemical energy from your arms. Or you could say something has potential energy, like it's sitting at the top of a hill and it's prone to roll down the hill in the gravity field of the Earth. That's actually called potential energy. But then there's also the energy that's just intrinsic in matter. One of the things that always gets me about this is that energy, light, light is sort of a form of pure energy. And us, matter, we're made of particles like protons and neutrons and electrons. They seem so different. They seem to have completely different views of the universe as well, which I think is one of the more interesting and disturbing things I know about in modern physics. Let's just think about the idea that energy and mass really are somehow the same thing. That mass is some coagulated, stored form of energy. That means the two of them, you can actually go from energy to mass and back and forth. And that's the famous equation that Einstein came up with, E equals mc squared. That in any amount of mass, there is an equivalent amount of energy, and the two are basically the same things. The universe actually doesn't seem to see much difference between mass and energy. As long as the amount is the same, it can exist in either form. And let me give you some examples of that. The way a nuclear reaction works, like a nuclear fusion reaction, is you convert some amount of mass into pure energy. Nuclear fusion actually brings particles together, slams them into larger atoms, and in the process, energy is released. So a little bit of mass is lost, but energy is produced. It also goes the other way. In a particle accelerator, you get more and more energy because of collisions of particles colliding together. They produce so much energy that as long as a given particle has that amount of energy, any particle can pop out of that reactor. And that's how we find new particles. As we get to higher and higher energies in a particle accelerator, just having that amount of energy around, the universe can manifest it now as mass. It takes a lot of energy. Equals mc squared. Energy equals mass times the speed of light squared. That's a lot. But energy and mass pretty much are the same thing. One of the ways the universe seems to do this is something called virtual particles. That if you have, just the energy, around you, the energy of space and time itself, there's sort of an inherent energy just in the universe. That energy can actually become mass. It'll actually form what we call virtual particle pairs, like an electron and its antimatter equivalent, a positron. Those two particles will just literally pop out of the universe because there's that amount of energy around, and then pretty much always they just annihilate each other. They just go back. Matter and antimatter annihilate back into pure energy. And this is happening all around you. Everywhere around you in space, these little virtual particles are forming and collapsing together all the time. Some of the more interesting things happen in the universe when those particles get separated. One example is around a neutron star. It can actually make a beam of energy coming off the magnetic poles of the neutron stars by having virtual particles be created and then accelerated by the magnetic field. So all of a sudden you have this energy that wasn't there before, produced by the virtual particles themselves. As you get to higher energies, say you have a very, very strong magnetic field, very high energy. Again, we find these around neutron stars. That can start creating lots and lots of these virtual particle pairs. And the more energy you have, the more of these little virtual particles you get, until space itself takes on an aspect of having mass. The density of these virtual particles right around a neutron star, even in empty space itself, would be about 3 times the density of iron. It's just unbelievable. So energy and mass really are the same thing. They're two sides of the same coin. They can be converted back and forth to each other, and the universe doesn't really care. It sees them both the same way. The thing about a neutron star, why do we call it a neutron star, for one thing? And I'm going to really oversimplify here, but basically, when you think about an atom, you have protons and neutrons in the nucleus of the atom, and then electrons are in orbitals around, farther away from around the nucleus. Amazingly, the gravity of a neutron star is so strong that it actually collapses the electrons into the nucleus. The gravity crushes electrons into the nucleus. And if you crush an electron and a proton together, one is negatively charged, one is positively charged, you will get a neutron. A neutron actually will naturally decay sometimes into an electron and a proton. You have an object that's mainly made of neutrons. There are some protons as well. And it basically has the density of an atomic nucleus. But it's about 10 miles across. I mean, that's like one big nucleus, 10 miles across. That's incredible. And because there was so much collapse involved in their forming, when you think about what they call the conservation of angular momentum, if something is spinning, and stars actually do spin, if you collapse that down, you actually spin up much faster. It's the classic ice skater analogy. You have an ice skater with her arms out spinning around, and then as she draws them in, you can watch that ice skater spin faster and faster. Same thing happens. But in this case, you actually have a ball that is about 10 miles across, spinning 500 times a second. I mean that in itself is just mind-blowing to think of, right? Something that big spinning that fast. Now, recently, neutron stars have played this important role in explaining something that we had no explanation for. They were very, very mysterious. In fact, there were some people that were wondering if we were actually looking at might be a signal from an advanced alien civilization. Those are called fast radio bursts. Now, fast radio bursts have been in the news for a couple of years because there was so much energy in these mysterious bursts of radio emission that we couldn't explain what was going on. So, for example, we would have, our radio telescopes would register a burst of emission, and that burst would last, say, a millisecond, 1,000th of a second. That's about how long these things would last. But in that 1,000th of a second, enough energy was radiated similar to what the sun puts out in a week, in a millisecond. And so we were getting these signals from, all over the sky. And we were trying to figure out what that could possibly be. How could you make that much of a tight burst of radiation in that small amount of time at those incredibly high energies? So the race was on to try to figure out what these fast radio bursts really were. Luckily, we have many, many things that are at our disposal to try to study these things. Right now, we have many high-energy telescopes that actually are orbiting the Earth that measure things like X-rays and gamma rays, the most energetic types of light. Light you only get if something is in the millions or billions of degrees. It'll actually emit X-rays and gamma rays. A wonderful thing is that we actually started to be able to kind of pinpoint to where these things were coming from in the sky. And as we did that, they actually seemed to line up with neutron stars. So neutron stars are most likely responsible for these fast radio bursts. Now, exactly what's happening is something that we don't really know yet, but it probably has something to do with almost like an earthquake. An earthquake, you have something, something in our crust shifts, and there are all these waves that go through the Earth. It's actually the way that we know the interior of the Earth is by studying those waves. We've never been able to actually take a sample of the fact that the Earth has magma all the way down until you get to at first a liquid metal core, then a solid metal core. No one's ever seen that physically, but we actually watch how these waves of compression go through the Earth, and we can put together what the interior of the Earth must be like. The same thing may be possible for neutron stars, but on a much more energetic scale. You have this ball of neutrons, incredible densities, incredible temperatures. And we think that there must be a crust of neutrons, that actually forms on the outside of these stars. And inside is probably a fluid of pure neutrons. We know this because neutron stars, as they spin, sometimes seem to sort of slosh around, almost like a water balloon. So we've modeled that to be sort of a crystalline thin crust. I can't imagine what that would be like. I mean, for one thing, the gravity would be so intense near that crust that it would just crush you into just particles, basically, on the surface of that neutron star. But if that crust were to have a flaw in it, and there was some sort of, a quake, it shifted somehow, it would send compression waves through the neutron star and release tremendous amounts of energy in a quick little moment of the crust actually sort of refiguring itself. So right now, our best explanation is that these amazingly mysterious fast radio bursts are probably neutron star quakes. And just like earthquakes have taught us so much about the interior of the Earth, now we're looking at the signal, even in a thousandth of a second. Take that signal, pull it apart, and try to find the structure that's going on inside that burst of radiation, and see if we can reconstruct what the inside of a neutron star is like. Neutron stars really are these real monsters. Unlike black holes, you can see them. You can see their surfaces. You can actually map how the radiation is coming off them. When it comes to really mysterious parts of the universe, but things that you actually can measure, I'd say go for some neutron stars. The closest neutron stars to us are very far away. They're on the order of many hundreds or thousands of light years. So luckily, they don't really cause any trouble for us. But the question I've always wondered is how close could you actually get to one of these things and make a measurement before you would just be fried by radiation? Or in the case of a neutron star, something stranger still. A lot of people are familiar with Einstein's famous equation E equals mc squared, which says that energy is equal to mass times the speed of light squared. And what that really means is that in any amount of mass, so if I think about like the mass of my little finger, there's a tremendous amount of energy. So if I could convert my little finger into pure energy, the nuclear bombs that were dropped on Japan, converted on the order of like a dime's worth of mass. So, there would be many, many nuclear warheads right in my little finger's worth of energy. But E equals mc squared also goes the other way. If you have a lot of energy, that basically starts acting the same way as mass. And it does so in something called virtual particles. If you have a lot of energy in a small space, the universe will start to actually create particles that have the same energy in their mass. So a lot of energy can actually become mass. And this is how our particle accelerators work. This is why you can discover new particles. Because if you just have a very energetic collision, like you take two gold nuclei and you slam them together, there's so much energy produced in that collision that it starts to pop off particles just from the amount of energy. And as long as you have enough energy, you can make any particle the universe has. The particles come off in all different flavors as long as they have the same amount of energy that collision is putting out. So neutron stars are doing something kind of like that. They're actually becoming sort of natural particle accelerators in a way just because of their mass. There is so much gravitational contraction that the magnetic field, the electric field and magnetic field of that star is actually compressed around this tiny little object now. So neutron stars have magnetic fields that are trillions of times more strong than a typical magnet you might have in your home, like a refrigerator magnet. It would actually pull regular matter apart, just the magnetic field. But there's so much energy in those magnetic fields. So think about E equals mc squared. There's so much magnetic energy right around a neutron star that the vacuum of space itself starts to make these virtual particles. And I was at a lecture one time, and this just blew my mind. This is what happens when you work at NASA, and you go into a lecture your colleagues are having, any day of the week, and they were saying that right around a neutron star, the density of space itself, the vacuum of space, right, a place where it's a vacuum, there aren't any particles otherwise, has about 3 times the density of pure iron. Just from that amount of virtual particles being produced by the energy of that magnetic field. So what's it like to fly around something where space itself has the density of 3 times of iron? What's that like? What does that look like? I would love to see what a neutron star looks like from a safe distance, and I'm not exactly sure what that is. When you're dealing with so much energy that even empty space becomes much more dense than iron. And once again, these are real. They're up in the night sky tonight. I mean, you can't see them because they're dim and they're small and they're far away. So it's not something we actually see in the night sky. But all around us, we're getting the radiation, the high energy radiation from these things that are real monsters. Our sun has this wind of high energy particles. This is something that was only relatively recently discovered. I mean, when you think about the fact that the very first satellites we put into space, starting in the very late 1950s, and 1960s, they realized that there was this source of radiation up there. There was a lot of particles around up in space. I actually had the honor of being next to this man named Eugene Parker. We have a wonderful mission named after him called the Parker Solar Probe. This mission is actually orbiting around the sun right now, closer than any human-made thing has ever orbited the sun before. It's really, really exciting. He was, I believe, 94 years old at the time of the launch. Usually, we only name spacecraft after people posthumously, after they've died. He was the one that basically predicted the solar wind and was the one that figured out how it worked. And of course, we're still figuring out a lot of the details, but they just couldn't think of anybody better to name it after than him. And so that was lovely. The source of these high energy particles and exactly how they get accelerated away from the sun is what we're studying right now. We know that this wind of particles, when I say high energy particles, I'm talking electrons and protons and sometimes as large as like the nucleus of a helium atom, something like that. And they get blasted through our solar system at 1,000,000 miles an hour in some cases. And so, we have this very high energy wind. It changes planets. It's responsible for Mars losing its atmosphere over time and becoming this kind of cold, dead desert. It's responsible for Venus becoming sort of this hellish thing that we know it. It actually blasted away all of the lighter molecules like water. And it left Venus with an atmosphere of carbon dioxide and sulfuric acid. And even Pluto, all the way out at the edge of our planetary system, Pluto is still losing tons of atmosphere a day, blasted away by this wind of high energy particles. The only reason the Earth is not really affected by it much is because we have a very strong magnetic field. And so, our molten metal core, all that molten metal moving around inside the Earth generates kind of a magnetic bottle around the Earth, and that protects us from the solar wind. But someday, the sun will actually, pretty much blast away our atmosphere anyway. So, planets change. And one of the important things about knowing about this wind is we have to understand our environment in space. The solar wind normally is at levels that humans can take quite easily. I know that some people that are into conspiracy theories say, how could we have gone to the moon because there's so much radiation in space? Well, the answer is we kind of got lucky with Apollo, because a normal day, the solar wind is a radiation level humans can handle quite easily, up in space or on the moon. Problem is that if you have a solar storm, a very, very violent event that unleashes lots of this solar wind, a lot of times we call these coronal mass ejections. The corona is the outer layer of the sun's atmosphere, and coronal mass ejection, all this stuff comes out at once. It's true that if a big one of those happens in the direction where astronauts are, unprotected from the Earth's magnetic field, they could die. I mean, it could actually give them a fatal dose of radiation. That is something that we need to consider. And it turns out that we got kind of lucky that, in between some of the Apollo missions, when no astronauts were up on the moon, luckily, we actually had events, solar events that would have endangered the astronauts. That's why it's hard to go to the moon and also to Mars, is to protect people from that radiation. It's not that hard to protect you from it. I mean, a good amount of water could do it, like if you had a water tank in your spacecraft and you could shelter behind that. It's just that you'd have to bring up a decent amount of water, and that's a lot of mass. Or in the case of the moon, I think if you could dig down just about 10 feet below the lunar surface, that amount of rock above you would shelter you. But then we need to bring, construction equipment to the moon that can dig a tunnel, right? So, I mean, there's all kinds of things we're considering as to how you would handle that. So what happens with shock waves is that you have, say, two binary stars close to each other, and they both have a wind of particles. In this case, we don't say a solar wind, we say a stellar wind, because we're talking about stars, but it's really the same thing. The main difference is that the stars that I was studying are very massive stars that have, anywhere from, let's say 20 to 50 times the mass of the sun. And they actually have really strong winds, much stronger even than the sun does. So when you have these two stars close to each other, these winds come off and they collide. And when that happens, literally the electric and magnetic fields, sort of entangle with each other, the particles collide together, and that creates a very, very hot area that we call a shock wave. As all of this stuff comes together, basically slows itself down as it collides, you get all of this heat and radiation emitted along that shock front. Those are wonderful shock waves that are created by colliding winds. Yeah. So one of the big challenges right now, especially as we consider putting astronauts back on the moon, is there a way to predict when one of these violent events is coming? The answer is yes, in several ways. So in the very simplest way, we actually have spacecraft. As I mentioned, there's a spacecraft orbiting the sun right now. There's actually two, the Parker Solar Probe and the Solar Orbiter from the Europeans. And we also have other spacecraft between the Earth and the sun. As one of these big belches of material, charged high-energy particles, comes out of the sun, it will hit different satellites that will measure how fast it's going, how much energy is being delivered. And usually in the case of say, the moon, the Earth has about a day or maybe 2 days notice. So you could say to the astronauts, hey, something's coming, everybody go shelter, as long as you had a good shelter there. But then there's the question of, can you predict it before it actually happens? And this, of course, is one of the huge goals all over the world of people called heliophysicists. Helio for sun, and then physicists. So people who are physicists that specifically study the sun. The sun is this incredible magnetic marvel. A magnetic field is generated by moving charges, right? So you think about like the charges in moving metal that generates a magnetic field in an engine. In the case of the sun is made almost entirely of hydrogen. But it is so hot on the surface that that gas has become ionized. Now, what that means is there's so much energy that electrons that normally orbit around a nucleus, the electron gets so much energy it just takes off. And that leaves two particles that are charged, an electron and a proton. Anything that has an electric charge, a magnetic field can bend. And so when you see these wonderful like loops on the sun and all of these beautiful shapes, that's the very hot electrically charged gas just following the magnetic field of the sun. The name for it, and it's kind of a confusing name, is plasma. You could actually see the shape of the sun's magnetic field, but it's chaotic. It's incredibly complicated. So you have these wonderful loops of magnetic energy, all this stuff following it. So how do you predict, when one of those loops is going to break open and actually like spew stuff out and create one of these big ejections? We're getting better at it, but it's still something that we don't understand. I mean, something that's simple about our own star. When is there going to be a really big storm? We can't predict it down to the hour. We can say there's a very active region here that looks like it might produce something, but there's no way to guarantee that. Actually, it kind of reminds me of the year 2012. Because I was having sort of a difficult year that year because people had this idea of the Mayan apocalypse. It was 2012. Apparently that was the end of some calendar cycle in the Mayan calendar. The idea was that something catastrophic was going to happen. And I would get calls. Seriously, people would call us at NASA and say, I don't want my pets to suffer. Should I euthanize? I actually got a call, somebody wondering if they should euthanize their pets. Other people would say things like, is the world going to end next month? And I'd say, look, okay, if I knew the world was going to end next month, do you think I'd be here in my office answering phone calls? I don't think so. And we kept telling people that there was really no reason to worry about anything. There was nothing unusual astronomically happening. The sun was in a naturally active period that year. Every 11 years or so, the sun becomes very active, and then it kind of gets quieter again. One of the reasons I know this is because I love to see the northern lights, the auroras. Those are caused when you get these charged particles in our atmosphere, and they create these beautiful glows around the poles. For us, that's really the only thing we really notice for the most part. What happened actually is that there was a colossal coronal mass ejection, one that would have actually been dangerous to our power grids here on Earth. It wouldn't have caused any damage to like people or animals or plants, but it would have actually dumped electric current into our magnetic field. And it probably would have taken down, a lot of power grids. It would have caused a lot of damage. The thing, though, is it went off on the other side of the sun from the Earth. And we had satellites out there in that other direction, out in the solar system, and they got knocked silly by this big burst of charged particles from the sun. And so we looked at that, and we were able to observe it and see what had happened and track it and all of that. We all kind of went, phew. The sun spins. It actually doesn't all spin at the same rate. The equator spins faster than the poles. It's not a solid thing. It kind of twists itself up. The sun, on average, spins about once every 29 days. And so we don't really know. There could be an active region that's about to blast, but then it could spin out of our view, and so we're safe from it. Or something could come, from the other side of the sun that we didn't see. There's all sorts of wonderful complexities when it comes to observing this phenomena we call space weather. The winds and the storms, but in this case, winds of particles and magnetic storms of magnetic chaos on the sun. It's a wonderful thing to think about that our lovely, gentle star up there is actually very dramatic and very volatile.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.